Today I am going to discuss about the UJT firing circuits. Last two classes we have seen resistance firing circuit, resistance capacitance firing circuits. UJT firing circuit is comparatively faster than resistance and RC firing circuits. Let's start. In R and RC firing circuits, power dissipation in the gate circuit is more, so efficiency of the circuit is less. R and RC firing circuit is too much complex and generally not preferred for automatic or feedback control systems. In those systems, generally some voltage is sensed, and based on that sensed voltage, a signal is generated to turn on the SCR. That becomes too much complex. That's why it is avoided. First, why the name is UJT? It is Unijunction transistor. You can see the diagram. Three terminals are there: emitter, base B1 and base B2. So two bases, one emitter. In this unijunction transistor, only one junction is there. You can see upon N-type base, a P-type material is dropped, forming a PN junction. Now the N-type material is lightly doped, so the resistance of this N-type material is more. And this resistance is divided in two parts. Resistance just above the emitter, or you can say doped P-type material, and resistance below the P-type material. This P-type material is generally placed close to B2 junction. So the resistance AB2 is lower than resistance AB1. And this resistance is AB1 or RB1 and AB2, that is RB2, is known as internal resistance of the transistor. The symbolic representation of this UJT is shown in figure B. Emitter B1, B2. The point A is known as eta point. Let's discuss the significance of this eta point. Now, working principle of this UJT. Two voltage sources VBB and VE are connected here. VBB is connected across two bases B1 and B2. VE is connected across emitter. Now this P-type material along with this N-type base is forming a PN junction. If anyhow we can break this PN junction, then we can say our UJT is on. When VBB is applied across this B1 and B2, current flowing through the VBB, B2, B1 is VBB divided by sum of the two internal resistances, RB1 plus RB2. If we are going to find voltage across AB1, then VAB1 is equal to that current into RB1. That's why in equation 1 you can see VAB1 is equal to RB1 by RB1 plus RB2 into VBB. RB1 by RB1 plus RB2 is known as intrinsic standoff ratio and represented as eta. Range of this value is 0.51 to 0.82. Our purpose is to reduce the value of this RB1 by RB1 plus RB2. As the region AB1 or the resistance RB1 is more compared to RB2. If anyhow we can reduce the value of this RB1, our transistor will be on. Now to reduce the value of this RB1, a positive emitter voltage is applied. Based on this emitter voltage, the junction P and N will be forward bias. Once the junction is forward bias, the region RB1 will be flooded with majority carriers. Now these majority carriers will be attracted by VBB, electrons towards positive plate and holes towards negative plate, and the carrier starts moving. So current will flow from B2 to B1. So you can see that if the junction PN breaks down, the p-type doped material and n-type base, if it is forward bias, then UJT will be on. And during that time, the potential of AB1 reduces. The reason behind it is that when positive voltage is applied across the p-type, then it will inject more amount of carriers across RB1, and as number of carriers are more in region AB1, so resistance RB1 will reduce. As it is a semiconductor material and is flooded with more number of carriers, so its resistance will reduce. So as RB1 reduces, RB1 plus RB2 will reduce, because RB1 is the major portion of this internal resistance. Then current will starts flowing from B2 to B1. We can say our transistor is completely on. Two conditions are there. Here, to make the transistor on, UJT on, we can see that if potential at that point A is more than emitter potential, then it will be reverse bias. Then we have to make potential at E more than potential at A, then only it will be forward bias. So VE or emitter voltage must be more than the eta VBB. That means potential across AB1. Now in this circuit, two resistances are inserted. In series with VBB, a load resistance is connected. This is because if our transistor is on and its internal resistance reduces, then nothing will be there to oppose the current flowing from VBB. Then VBB will be short circuited and high amount of current will flow to damage the DC source VBB. Across emitter terminal, a resistance is connected to control the emitter voltage applied across UJT transistor. If we are increasing the value of this RE, RE is a variable resistance. If RE is increased, then voltage across emitter terminal will reduce. If RE is reduced, then voltage across emitter terminal will increase. And if this V is more than VAB1 or eta VBB, then our transistor will be on. So two resistances are required: load resistance to avoid the short circuit and RE to control the emitter voltage. Now in the circuit you can see PN junction is represented by a diode that is valid. That P-type doped material is shown as anode and N-type base is shown as cathode. Rest of the circuit remains same. RB1 is shown as a variable resistance. Reason behind it is that when the diode gets forward bias, then emitter will inject more amount of carriers towards AB1 and it will be flooded with more carriers, and resistance RB1 will reduce and our UJT will be on. So you can see the direction of current from VBB, B2, B1 back to VBB. So this will be our power circuit. Now VE, emitter, diode, RB1 back to VE. This will be our triggering circuit of UJT. Now let's discuss the VI characteristics of this UJT transistor. Here you can see along positive y-axis it is emitter voltage, along x-axis represented as emitter current. Now by varying the value of RE, slowly the emitter voltage is increased. So at P the emitter voltage is 0, now the emitter voltage is increasing. So as soon as emitter voltage increases, emitter current will also increase. But initially the emitter current is negative and it will come to 0 at point S. At this point, the movement of carriers in opposite direction or leakage current is removed. So PS is leakage current flowing through the transistor. Further, if emitter voltage is increased, then emitter current will increase. From S to B, we can say our diode is going to be forward bias. After B, if voltage is further increased, then diode is completely forward bias and the transistor is on. Just like thyristor, here also after B, current increases but voltage reduces. So this region is known as negative resistance region. This is because of more number of carriers participating in the conduction process and resistance of the UJT reduces, current increases and voltage drops down. This voltage will reduce up to point C, that is known as the valley point. B is the peak point. From peak point to valley point, current will increase and voltage will reduce. Now after valley point, if further voltage is increased, then current will increase and resistance will also increase. So this region is saturation region. This is because of repulsion of more number of carriers. Resistance of the complete junction increases. So we are not interested in saturation region. We will not discuss this in more detail. We will concentrate our discussion towards negative resistance region. In this region, we have seen that after B, current increases. Now this current, if it is applied across gate of the thyristor, then the thyristor will be turned on. So this will be our region operation of triggering our SCR. So this UJT can be used in triggering circuit. So in BC region, the increase in current is applied across gate of the thyristor and thyristor will be on. So our operating region for triggering the thyristor using UJT will be BC. Let's again discuss the different points of this graph. B is the peak point. At peak point, the voltage is known as peak voltage and current is known as peak current. C is the valley point. At valley point, current is valley current. In PS region, negative current is there. That is because of the leakage current. In SB region, PN junction is going to be forward bias. In BC region, it is forward bias and current has increased. Negative resistance region. CQ region is saturation region. So BC region is our focus and will be used for triggering our SCR. Now, how much voltage must be there across VB to turn on UJT? You can see the circuit VE, RE, diode, RB1. The emitter voltage equal to voltage drop across the resistance RE, then voltage drop across the diode, then voltage drop across AB1. This voltage AB1 is variable and depends upon eta as well as depends upon RB1. So if VE is equal to or greater than NVBB plus BD plus I into RE, then we can say we will be able to achieve this negative resistance region for triggering the SCR. So today we have discussed just basic working principle of UJT and we have concluded that in the negative resistance region, current increases, voltage decreases. So that pulse can be applied across the thyristor to turn on. We will see this application in next class. UJT triggering circuit or UJT oscillator circuit for SCR. Thank you.